I'm very proud to welcome you to our seminar, Fundamentals of ESD Protection. Before we start, let me share with you a little bit background. Around 2 years ago, my team of application engineers created our ESD application handbook with focus on protection concepts, testing, and simulation for modern interfaces. We covered a broad range of different applications in that handbook, focusing on communication, computing, automotive, and industrial. And strive also a lot of interfaces like USB, HDMI, MIPI, and IVN interfaces like CAN, LIN, etc. I'm sure a lot of you already received this book. It is designed for you, from engineers to engineers. The ESD handbook is part of a series of technical handbooks we have from the Nexperia series, also the Power application handbook with focus on MOSFET. We are working on a new handbook with focus on our logic products and applications. Some weeks ago, we launched the ESD Automotive edition. PDF file is already available on the internet. A hard copy version will be available soon. Our second seminar on Thursday will focus on automotive interfaces. The idea of Nexperia Encyclopedia is to share with you, our customers, our technical knowledge and application insights, which we are building up when we are talking with you and learning from each other. Now, let me introduce to you the presenters. Dr. Andreas Hardock, Application Marketing Manager for ESD, working for Nexperia, received his diploma from the Julius Maximilians University, Würzburg, and his doctoral degree from Hamburg Technical University in 2010 and also in 2015. In his research, he worked in the field of signal processing on filters and couplers based on vias. Since 2015, Andreas has been working in the automotive industry for Bear Heller and Continental, where he was involved mainly in ESD and EMC topics. In July, Andreas joined Nexperia with the main focus on ESD and automotive and high-speed application. Together with Andreas, Lukas will be the key presenter. Lukas Drömer, product manager, protection and filtering from Nexperia, received his bachelor degree from German Nord Academy as a company-sponsored student of NXP Semiconductors. Since 2018, Lukas works for Nexperia as a product manager for ESD protection filtering devices with a clear focus on automotive IVN networks such as CAN-FD, infotainment, and Open Alliance Ethernet. As mentioned, at the end, we will have a Q&A session, so please feel free to type in your questions. We will collect all questions and send out a document with all topics. Dear Lukas, now let's move on to the real important technical stuff.
Olaf, thank you very much. So again, a warm welcome from Andreas and me. And today we'll talk about the fundamentals of ESD protection, the why. So why do we have to end an ESD? And then we will move on more on the measurements and characterizations and really give you a brief overview. What are the factors we have to consider when choosing right ESD protection? And then later on, we will have our Q&A session. The why of ESD protection. So ESD is the abbreviation for electrostatic discharge. And that is a sudden discharge that happens between persons, devices, components. So it's a triboelectric effect. And the critical thing about this discharge is that it's causing malfunction. So it really can destruct electrical components and cause those micro-level damages on the gate oxides or other physical layers. And the critical problem is we cannot detect those damages easily. If we take a broader look, so what is the threat of ESD? So it's not about the electrical design, but basically we can see ESD threat everywhere. In this graph, you see the y-axis representing the voltage in kilovolts. The x-axis represents the relative humidity in percentage. And key takeaway here is that, yes, different materials have different potential of ESD, but what is very critical is the humidity of the air, for instance, in production areas. So in a production area, we want the air to be as dry as possible, but if the air is very dry, we have more charge can accumulate, and we have higher ESD potential. So that's a conflict we have, and therefore we need special concepts to prevent this damage shown before. If you're talking about ESD level, we have to distinguish between the device level on the component itself and on the application level. And now Andreas will move on and talk about this more.
Thank you, Lucas. So, as Lucas said, we have ESD, and ESD is happening everywhere in our daily life. So, and for us, for hardware engineers, we have the ESD especially to consider in production and in an ordinary usage of the device. And so, therefore, there's two levels of ESD. One is the device level and one is the system level. And we want to talk about both today. So there is the question, if you're taking care of ESD, you want to be prepared for this. And in order to do so, you need to kind of simulate this event, and it's usually is done by compliance testing in EMC labs. And for the device level, it's then important for any kind of components, electronic components on our PCBs, so ICs or also other components that needs to be considered here. And there is typically three standards you need to consider. The first one is the human body model, and the machine model, and the charge device model. We will talk about all three in later on. So, but then there's a system level view, and this is a completely different view. You do not look on every device, but you look on the total electronic modules. For example, an automotive cluster or display module, or mobile phone, or also complete PC. So from this perspective, from the perspective of the ESD protection vendor, as Nexperia is, we will look on the both, so on the device level, but with a big focus on the system level here. So we will go on the device level, and here, as we said previously, we have the human body model, which is very popular in use. So here it's models or simulates the discharge of a human body to a grounded device, for example, an IC. So, and therefore it's a low current but a long duration, and this is due to the low, so to say, conductivity of a human body. So it's to replicate this, we have an IC network with 1500 ohms and 100 picofarad, and it's applicable for all semiconductor components. So we then have as a second one, the charge device model. This is different to a human body. It's has a very high current and a very short pulse model, and it simulates the process of charging or discharging from a product to a ground environment, for example. So if you have a component or a module which is handling in a plastic fabrication, and then you possible have to consider a possible grounding to any metals here. And in addition, a third one, there's a machine model also known, but we do not want to get into real details here because this machine model is not applicable anymore. In later years, it was found that it's outdated and it's not saying nothing about real applications right now. So this was the three models on device level, and then we will move on to system level robustness.
Thank you, Andreas. So what you see here is the IC 61000-4-2 pulse. And so this is the pulse that the system expects to see in reality. And if you see here, we can actually see two currents. The first one is a very rapid, sharp first peak. which you saw on the CDM model. And then we have the second discharge, which is also called the shoulder, which contains the vast majority of the current. And it looks similar to the human body model. So you can see this as superposition of both human body model and charge device model. And what is critical here, so as I said in the beginning, ESD events can cause malfunction and really destroy the physical layers. And if we can see two different failure mechanisms. So the first one is similar to the charge device model. And here you can see that this high peak current really destroys the gate oxide and causing this malfunction. The shoulder, or the second peak, containing a lot more energy and has also longer duration. This causes really electrical overstress. So here we have this thermal destruction. So when you see, or people are talking about an EOS failure, this comes from this shoulder or from high surge event. But in both cases, we have the physical layers destroyed. And the problem again is, or to explain it even further, why we cannot detect it. So to see those damages, you have to run a disrupted physical analysis. And here you can see between the gate and the source how this physical layer is damaged because of ESD stress. But if you see on the resolution with a normal eye or even with a microscope looking on the PCB, you will not see this damage. And that's why, again, we need special and good concepts to prevent this damage. Then another larger picture here also on the physical layer, where you see really the metal layer is burned, and to take this, it's critical. So we have special concepts for ESD protection, and then we will start first with the internal concepts of ICs.
Yes, if we want to have all these damages Lucas talked about in previous slides, we need to do something against it. We need to be prepared for that, and there are some strategies are done on IC level, and we have here one of this. So on the right side we see the picture with a internal topology showing of a typical IC. So, and we have on so we have an I/O pad here, which is the input of the IC. So this is the possible input of an ESD event here, and you see so that the IC vendor is prepared a little here. There's a clamp placed to clamp possible ESD to ground here. And when you look further on the link, there's a resistor placed, which might help you or might not help you here. And there are some additional clamping protections here to protect your complementary CMOS, for example. And to protect the total device here. But due to cost reason and to simplicity, it's here usually only done for a device to survive the package and handling process. So it's typically not done to survive this system level robustness. So when one of the IC vendors is saying to you, we have a robust ESD robust device, this typically means, okay, this is robust against packaging and it's robust for handling, but it's not usually meant to be robust against in a system on a system level. So an additional example, and this is shown on a smaller component here on a MOSFET, a P-channel MOSFET, and here we have also some protection, built-in protection, so to say, for the MOSFET. We have an ESD protection, which is capable to handle up to 2 kV, and this is a human body model, so it says to you that this device is ready is protected for packaging and handling process. Yeah, but not on a system level where even more and even higher ESD voltages can occur for sure. So, and what about the future? What about the ICs itself? And we all know that the and also in mobile, but also in automotive applications, the trend in semiconductor industry is following the Moore's law, and this means that even so the functional density is increasing here, and since when you consider that for an internal ESD protection you need a certain amount of area, and it's indicated here with a red point here, and if you increase the density, the functional density in your IC, that means that the gate oxides will decrease, and so there's at some point you reach so to say the break point where the space for your ESD protection will be the same or even more as the functional space, and so then you will get in problems, and therefore the human multimodal target will be reached, and it will be probably also adapted in future years. But this means with high increasing data rates, the ICs, and this is the takeaway here, the ICs will getting more and more sensitive, and there is an increasing demand on an external ESD protection here, and we also have a really real example for you here shown on the right side. So here is one IC is shown. This is a CAN bus, CAN transceiver, and we placed on a typical PCB with a connector here in front, and on the data lines here, on the differential lines, we placed an external ESD protection here close to the connector, which is also very, very important to have it here close to the connector. And in the case of an ESD event at the connector, the ESD protection will turn on, and at this moment it will take the biggest or the bigger amount of the current, of the ESD current. So and for your IC there will be only a small amount of current left. So it's protected very well here. We with this topology, having the ESD protection close to the connector, we have a current divider topology, which is also very helpful here. And to show you also some real numbers, we made these tests with several CAN transceivers. You see here on the left side, and we did the test without and with an external ESD protection, and we see here that without an external ESD protection, the ICs behave different. They have different ESD robustness levels. It differs from 8 to 12 kVs here. But if we place an external ESD protection here in front, so we have 30 kV ESD robustness here, which is very constant, and it doesn't depend on any specific CAN transceiver anymore. Okay.
So I think we can all agree that external ESD protection is really important, and we had enough proof on the previous slides. So this brings us or leads us to the question: if we want to choose an ESD protection device as engineers, which are the factors we have to consider? And that's coming now. So if I have a design and I need a new ESD protection, or I want to choose the best ESD protection as an engineer, what do I have to focus on? And first, I might ask myself, what is the PCB space I have available, or what PCB space can I spend for my protection? So this narrows the size and the footprint of the device. And then I can ask myself, do I want to have a leaded package, or is also a leadless package an option to have better RF behavior? If it comes to leadless packages, does my company have a quality policy for assembly? Do I need side vertical flanks for automated optical inspection? So those are the, let's say, the external factors. I have to consider also the number of signal lines I want to protect. And if those questions are answered, this brings us then to the electrical performance. And there we have a lot of parameters that give us an indication which ESD protection is the right form application. And then on the following slides, we will explain them a little further. So starting with the number of signal lines, what you see here is a USB 3 connector. So this is the bottom side of the PCB. You see here that the high-speed lines run through this area of pins. And then on the other side, you will see the ESD protection device protecting multiple lines at the same time. This is an example, but in real life, maybe those factors of multiple line protection are less critical. So if we protect multiple lines with one device, we have benefits like mesh capacitance, we have mesh inductances, etc. But maybe we want to have even better level of protection, and we might consider a single line protection here in the case of a Type C connector. With single line protection, we have the advantage that we can position the ESD protection much closer to the connector. And then, as Andreas shown before, if we position the ESD protection right at the connector, the whole cell works as a current divider, and we have lower clamping voltage, resulting in better level of ESD protection. We often get questions about capacitance matching. Do I sacrifice something? Do I have disadvantages when using single line protection? Not really, because in terms of capacitance matching, the relative deviation is similar. So if I have a canvas with 20 picofarads, and I may have a USB bus with 2 picofarads, the deviation is similar. And if I have a high-speed bus where I need lower capacitance, in effect, the absolute deviation will be lower as well. So then, maybe on a bus where we use 2 picofarads, now the deviation is only 0.2 picofarads. And this impact is really minor and less critical in real life applications. Then coming to the one of the main parameters, the reverse working maximum voltage, VRWM. This voltage is indicated at room temperature, and this voltage is the guaranteed voltage where the ESD protection is not activated. Again, at this voltage level, the ESD protection is not operating. To get an indication when the ESD protection is operating, we have to take a look on the row below, the breakdown voltage. The breakdown voltage describes the transition from, let's say, a standby mode to the real operating mode of the ESD protection. And then you can get the current straight to ground. So that's an important distinguishment we have to make here. ESD. As we said before, we have to distinguish the device level and system level, but of course, we want to know what is the device level robustness itself. And here we have different norms. So at the top, we see the setup from the IC 61000-4-2, where we apply here a contact discharge. We have air discharge and contact discharges, but we only perform contact discharges, or mainly, because they are highly repeatable. I showed the graph of the influence of the relative humidity. If we have an air discharge, we can, we have a high dependency on the air condition, and that's why we urge to only focus on contact discharge because of its repeatability. So then you see the table with the ESD gun, and then you have the vertical or horizontal shooting on the coupling planes. And what we then do is we measure the IV curve. And what is interesting here, so if you measure this curve, if an ESD device is not activated, it's high ohmic, low capacitance. And if it's turning on as ESD device or starting to even to fail, then it becomes low ohmic and has a high capacitance. And with this IV curve, we have a clear indication until which level the ESD device withstands. So looking on a data sheet here for a CAM protection device, we see here the different norms, and then we see here that this device show a maximum ESD rating of 30 kV. So this tells us the device itself, the ESD protection device itself, presents 30 kV, which is very sufficient. We have a high safety margin, but again, this number here, 30 kV, does not mean that this device is protecting the system with 30 kVs. It's not telling us something about the system level robustness, only about the device itself. And if we want to have an answer on the system level robustness, we have to focus on the clamping voltage, which is the next parameter.
Yes, thank you, Lucas. So as Lucas said, so at least the ESD robustness and this 30 kV, which Lucas has shown on the previous slide, they say to you anything about how much or how robust your system later on will be. Therefore, we need to look on the clamping voltage. And the clamping voltage is basically the thing or the voltage which the IC, your PHY, your CAN transceiver, your Ethernet transceiver, or whatever you're using service is seeing after the ESD protection. So and here is an example shown on the right side. Which in the graph of a clamping voltage you can find in any data sheet. And so here this is an example based on a 8 kV pulse waveform of, and the waveform is according to IC 61004-2. So it's this pulse form Lucas described previously at the beginning of the presentation. So if you are applying 8 kV maximum peak voltage pulse here on your system, and you are using this device here, this ESD protection, your IC will see this voltage. And at this 24 voltage of the clamping voltage is taken here at 30 nanoseconds. This is according to the pictures here on the left side, and this is basically to or it's a per definition that's defined to be by history. So earlier on, it was found that some LIN or CAN transceiver are not very fragile against the first high voltage peaks. So they are needed to be protected against this the second shoulder. So and there it was defined. So we will take the clamping voltage value for the datasheet after 30 nanoseconds. So this is the takeaway here, that the clamping voltage, and especially the graph you see in the datasheet, is the voltage your device, your IC, is seeing after the ESD pulse is applied to your system. And so one question can be here is how to measure this curve, and this is we will cover in a few slides next. So here you see the block diagram of a test setup for these measurements. You see on the left side the ESD generator itself, and here is the DUT, the device under test, meaning the ESD protection we want to analyze, and we want to look at the voltages, the clamping voltage with the oscilloscope here. And in order to protect the oscilloscope against too high voltages, you might also use an attenuator here for DTP, for example. It looks very easy on the block diagram level, but it's when you really doing these measurements, it turns out that it can be very tricky here. And one reason is that in ESD there's a highly dynamic pulse, especially in the first time after the strike. So in the first 1 or 2 nanoseconds, we have the highest dV dt or di dt also, and it means that we also have the ability of a high coupling energy. And coupling energy means by any electromagnetic wave. So we need to prevent this, and we're doing this by putting the ESD gun into a shielded chamber. And you see on the right side here, and we cut a hole here, and on the other side of the hole, we assemble such an SMR adapter to get contact to the tip of the gun. And here we screw our device under test, so meaning our ESD protection on this small test PCB, and then here we measure the voltage with the oscilloscope. So also a few short statement to the oscilloscope, or to how to measure this voltage with the oscilloscope. It's on the right side you can see some curves of the clamping voltage you can find on data sheets, and yeah, this is done with a oscilloscope and a low sampling rate here. And what we've done, we re-measured these devices, these ESD protections, with high sampling rate here, at least 2 gigahertz, and what we see is very surprising, or can be very surprising here. So what we measured is at the beginning here, at the first nanoseconds, so to say, of the ESD strike, we measured voltages up to 223 volts here, using this high sampling rates of the oscilloscope. And if you look on the data sheets, it's not really good to see, but it seems that the first peak is not even taken into account, so it was lost. So this is one example for you, just to use an oscilloscope with a high sampling rate. So we have also another electric parameters we need to consider for the ESD protection, and Lucas already introduced this slightly, and this is the dynamic resistance. And in order to measure this dynamic resistance, it's kind of also tricky and not very trivial, and for this we need this transmission line pulse, this TLP test. And the idea behind this TLP testing was first the bad repeatability, so to say, of the ESD gun or the ESD event itself. Lucas told already about at the beginning, so we have really high tolerances in the ESD pulse itself. This is one thing. We have high impacted of the environment, basically on the humidity of the air, for example. And in addition, there are also kind of big differences, or can be big differences from the ESD gun vendors also. And in order to prevent all of these, this TLP was invented, and this is the basically test setup, or the block diagram of this method. We have on the left side the voltage generator, and what we do is that we load up a transmission line, a 50 ohm transmission line here, and if it's loaded, we close the switch, and then the entire energy is transmitted from the transmission line on the left to the one on the right side. And it's also a 50 ohm transmission line, which is very good. This is impedance controlled system, and then this pulse is flowing here through your device under test. And what you do here, you measure the voltage at your diode, and also the current which is flowing through the diode. So we have a very controlled system here, impedance controlled system, and some possible reflections are which are present in ESD and are avoided here by using this setup. So this is the real equipment what we are using, and on the left side we see the voltage generator here, and here the left bottom side we see the contacts. So we are So the contacts are very thin or very fine, let's say. So it means that we can contact on a bare die even, or for sure also leaded packages, or any packages can be contacted here and tested. And in addition, we also use this TLP testing to analyze the internal ESD protection of the PHYs, which is also somehow important to know, and for troubleshooting we use this also. And so what you get from this TLP, and what is the result? It's typically you are producing such pulses which rise time of 1 nanosecond and a pulse duration of 100 nanoseconds. This is the normal TLP, but there is also a very fast TLP is used with a 3 nanoseconds pulse time, which is only for some special applications, let's say, in use. In 90-95% you're using this typical pulse with 100 nanoseconds. So as we said previously, we are measuring the current over the diode and also the voltage over the diode. And we are looking here in this time window between 70 and 90 nanoseconds, and we do averaging here in this time window in current and voltage. And this average values will be placed here on the IV diagram. And since we're not doing only one pulse, but it's a number of pulses with increasing voltage, and so according currents, we will get some more points here on the IV curve. And this IV curve is, let's say, the IV curve for pulsed system. And from this IV curve, you can predict an electric behavior of your ESD protection. So shortly to the slide before, here on the right side in this IV curve, we also see the dynamic resistance. To get the point here, the dynamic resistance is the dV over dI. So it says you something about how good is the ESD protection here. And if you're having higher dynamic resistance, so you are here on the right side, your device is worse. And the goal is to get the steepest curve here as possible to get the best ESD protection. Okay, so what we see here is a real example from real device. And these devices are from Xperia all, but you see also here the evolution of ESD protection since last years, so to say. So what we see here is the old PSD1 can, this old part, so to say, and then it has here a very high dynamic or comparable high dynamic resistance, and so it's protecting your device not that good that the PSD2 can, which was developed after the old one, and which are showing you even or smaller dynamic resistance, which means better ESD protection. And right now the latest products we have in our portfolio is the PSD IBN series, and this is improved in the dynamic resistance even more. And what we see also here is that the behavior here is very constant. So there's no jumps or anything seen. So it's a constant behavior in a very big dynamic range up to 70 or 80 amps. So what we see also here that when we look at in the region here, we see some different behaviors, some different topologies. And what it's all about this, we will cover on the next slides. So this slide you probably, or this picture you have seen probably already in some data sheets or during your work as design engineer. So this is a typical classical Zener topology, the characteristics of the Zener topology. This is a bipolar device. So we have two ESD diodes here in series, and what we see is the reverse case for both of them. So we see here also the voltages in the graph Lucas told about. So we will see the standard voltage and the breakdown voltage with the corresponding currents here, and also for the negative side. And what we see also is the clamping voltage, with the, as we learned in previous slides, very important here for your device, for your IC to protect. But what we also have is, so to say, snapback devices, and they are different from having this, let's say, Zener topologies or varistor topologies. So the snapback devices are behaving different, meaning that if you are achieving a certain voltage, and it's called the trigger voltage here, VT, so your device will not behave like a Zener here, but it will snap back to another voltage level, which is called the holding voltage. And from this point of view, it behaves then with increasing voltage similar to Zener. But the main difference between them is that is shown here with the yellow arrow. Is that the benefit is that having this snapback device, you can lower your clamping voltage very significantly. And as we learned previously, the clamping voltage is the key to protect your your IC. And having very low clamping voltage means to protect your IC better. And what we want to say here is that the classical Zener topology is not better or worse compared to this new snapback. It's different one, and it's some applications, and we will refer to this application in the next webinar on Thursday. It might be very good to have this snapback topology and to benefit from them.
Thank you, Andreas. So running through again, or just have a quick recap. So we discussed about the fundamentals of ESD protection. So what is ESD itself? What is the problem we have to deal with ESD events? And we then talked about the difference between device level and system level that we always have to distinguish here when we think of concepts of ESD protection. And then we went on and covered some selection criteria. So talking about number of signal lines, we talked about the electrical parameters and how we characterize them. And that's the theory, let's say, for session one. We will now just make a quick view on our next Criterion lab, what we're doing as well. What are different measurements that we can do here that help in to have an application understanding, and then we will move into our Q&A session. So in our next Criterion lab, we do only perform those measurements Andreas and I presented before, but there's a lot of more. We have an EMI scanner, for instance, and there's also a lot of simulation we can perform. So for instance, system efficient ESD design really helps us to predict the system level robustness of the device, and performing simulations often saves a lot of time, and it's also less cost intensive, and that's something we just want to remind here, that you don't only have to perform measurements, but you can also perform simulations. Again, the MI scanner, because it's we're a little bit proud of it, is special equipment, not common to every company working on electronics. So what you see here is you have this robotic arm moving this H-field probe, and with an EMI scanner, so we measure the electromagnetic interference on the PCB, so the current density on the traces. And what we get then, if we have this ESD pulse running, distributing across the PCB, we can take or film a video. So here you see a screenshot, and on the left-hand side you see a PCB without external ESD protection, and there you can see that this red color here, so red color means we have high current density, is running from the connector through the traces into the IC, and here it can really destroy the file in the physical layers, and we have this micro damage. And that's something we don't want to have. If we use external ESD protection, we can see that only a minority of the current is running here into IC. We still, of course, see some current here at the 5, but there the internal ESD protection, as Andreas explained, can work and survive. But the vast majority of the ESD current and voltage is covered by the ESD protection, working as current divider, and is then guided to ground. And it's here moving up because in this PCB the ground connection is here at the top. So it's another kind of measurement that really helps us to get a better application level understanding and then give design recommendations. Besides the automotive ESD handbook that Olaf introduced in the beginning, we also have a broader set of collaterals and articles, white papers, product information you can find on our Nexperia web page.
I would like now to thank all participants for joining this ESD Fundamental Seminar. So for today, I would like to close this meeting. Thanks all for your participations, and Team Nexperia says goodbye and stay healthy in these days.
Thank you very much.
Thanks, bye-bye.